Good morning. In today's class, we are going to discuss about electromagnetic waves. We already learned a session on electromagnetic waves. Today in this class, we will go in detail about this electromagnetic waves. We know that the electromagnetic waves do not need matter to transfer energy. It can travel through vacuum. And how these electromagnetic waves are produced? They are made by vibrating electric charges and can travel through space by transferring energy between vibrating electric and magnetic fields. So the vibrating electric charges can produce electromagnetic waves, and these electromagnetic waves travel in all directions with the speed of light, that is c 3 into 10 raised to 8 meter per second. Let's discuss how we can produce electromagnetic waves. From the word itself, it contains both electric field component and magnetic field component. And you have studied about electric field and magnetic field in your lower classes. What is electric field? Electric field is the region around an electric charge, around a stationary electric charge, in which other charges can experience a force of attraction or repulsion. And we can find out the intensity of electric field at a distance r from this point charge with the help of the equation E is equal to 1 by 4 pi epsilon 0 q by r square. That means electric field depends on distance. Similarly, what is magnetic field? You know that there is a magnetic field around a current carrying wire. And you can find out the value of magnetic field with the equation vector B is equal to mu 0 I by 2 pi r. So electric field is equal to 1 by 4 pi epsilon 0 q by r square, and magnetic field B is equal to mu 0 I by 2 pi r. So in both these cases, you can see that electric field and magnetic field depends only on r. That's about a stationary point charge q and also about the current carrying wire or conductor. Now what happens if the charge is accelerated or if the current varies with the time? An electromagnetic wave is produced. So a moving charge creates electromagnetic wave. Moving charge means it constitutes current, isn't it? So any moving electric charge is surrounded by an electric field and a magnetic field. So electric charge means there is electric field around it, and if it is moving electric charge, there is a current and there is a magnetic field around it. So moving electric charge can produce electromagnetic waves. So when an electric charge vibrates, the electric field around it changes and it creates a changing magnetic field. You can write the Maxwell's equation here for the verification. That is del cross B is equal to, there is dou E by dou T, isn't it? So here the electric field is changing with the time. So dou E by dou T contributes to B. So the electric field, varying electric field, creates a changing magnetic field. Also, the magnetic field, change in the magnetic field creates electric field. Del cross C is equal to minus dou B by dou T is there, isn't it? So the varying magnetic field creates an electric field. So in that way, both the electric field and magnetic field create each other again and again. And this variation propagates as an electromagnetic wave in all directions. Here the figure shows only the movement along one direction, isn't it? So the wave is moving along this direction. See, the blue color denotes the magnetic field and the yellow color denotes the electric field. So the varying electric field or varying magnetic field creates both and vice versa. And this variation travels in all directions as an electromagnetic wave. And these electric and magnetic fields vibrate at right angles to the direction of wave. See, here you can see this is the direction of wave. And you can see this, and the magnetic field as well as the electric field is perpendicular to the direction of the wave. So that we can say that this electromagnetic wave is a transverse wave. So the electric and magnetic fields vibrate at right angles to the direction the wave travels. So it is a transverse wave. Now how we can represent a wave, an electromagnetic wave? We can represent an electromagnetic wave in the form of a plane sinusoidal wave. So here the electric component and the magnetic field component are given. See, vector E is equal to E0 sin kx minus omega t j cap, and vector B is equal to B0 sin kx minus omega t k cap. Here the wave is traveling along the positive x direction. So that electric field E is in the y direction and magnetic field B is in the z direction. So both electric field and magnetic field are perpendicular to the direction of propagation of the wave. Here the wave is propagating along x direction. So we can represent the components of electric field and magnetic field as E equal to E0 sin kx minus omega t j cap, B is equal to B0 sin kx minus omega t into k cap, where k is called the wave number defined by the relation 2 pi by lambda, where lambda is the wavelength of the electromagnetic wave. Omega is the angular frequency. Omega is the angular frequency of the wave, which is equal to 2 pi f, f being the frequency of the wave, or omega is equal to 2 pi by t, where t represents the period of the wave. Also we have the relation C is equal to nu lambda or lambda by t, where C is the velocity of the electromagnetic wave in vacuum. So in this way you can represent a plane electromagnetic wave which is traveling in the positive x direction. with its electric field component and magnetic field components are given. Now this is the equation connecting electric field and magnetic field. That is E by B is equal to C. Here E and B are the instantaneous value. Here in the last slide we had seen that E equal to E0 sin kx minus omega t and B equal to B0 sin kx minus omega t, isn't it? So E0 and B0 are the amplitudes. So you can get the velocity of electromagnetic wave by the relation E0 by B0 is equal to C. Now we are going to have the derivation for the energy propagated by the electromagnetic waves. We know that the electromagnetic waves carry energy, and as they propagate through space, they can transfer that energy to the objects in their path. So the electromagnetic waves transfers their energy as they propagate from one place to another. The energy per unit time, per unit area is known as the energy flux, and this energy flux is given by Poynting vector represented by vector S. So the rate of flow of energy in an electromagnetic wave is described by the vector known as Poynting vector given by vector S. See, in this picture you can see that the wave is propagating along this direction, that means positive x direction. Electric field in the y direction and magnetic field in the z direction. So electric field and magnetic field are perpendicular to the direction of propagation of the wave, and the wave is moving with a velocity c, and the energy transferred by that wave is represented by the Poynting vector S, given by 1 by mu 0 into E cross B, where B by mu 0 is known as H. So you can rewrite the equation as E cross H. And Poynting vector is a vector quantity, isn't it? So vector quantity means it will have a direction. What is the direction of the Poynting vector? It's the perpendicular to both E and B. See, Poynting vector is given by 1 by mu 0 into E cross B. So Poynting vector is perpendicular to E and B. That means perpendicular to E and B means the wave is propagating along x direction. So its direction is the direction of propagation, that is E cross B. So energy flux density, which is known as the Poynting vector, is the energy transmitted through unit time per unit area. What is the energy transferred by an electromagnetic wave in unit time per unit area is known as the Poynting vector, which is also known as the energy flux density, given by S is equal to 1 by mu 0 E cross B, and we can find out the value of Poynting vector by substituting the components E and B. Let's have a look on another term which is known as intensity. Intensity of the electromagnetic wave is defined as the average energy flux density. See, energy flux density is the Poynting vector right? So the average energy flux density is known as intensity. So what does it mean? Both are having the same unit, isn't it? Average energy flux density as well as energy flux density have both the same dimension or same unit. That means intensity and a Poynting vector have the same dimensions. That is energy per unit time per unit area. So that energy per unit time, that is per unit area. That means the unit is joule per second per meter square. I repeat, Poynting vector is the energy flux density and intensity is the average energy flux density. Or it can be written as average power per unit area. Average power per unit area, so that intensity has another unit, watt per meter square. See, here in the picture you can see that the electromagnetic wave is passing through a block, and this block is having an area capital A. So we can calculate how much energy has been transferred by this electromagnetic wave to this area. From that you can calculate the energy transmitted per unit area in unit time. Now we are going to calculate the value of S. So in an electromagnetic waves, let E be varying along y-axis and B along z-axis, so that the wave is propagating along x-axis. So you can write E as E0 sine kx minus omega t or omega t minus kx. And B as B0 sine omega t minus kx or sine kx minus omega t into k cap, showing that electric field along y direction, magnetic field along z direction, and the wave is propagating along x direction. So what is S? S is 1 by mu 0 E cross B. So we can do the cross product of E and B here. J cross k cap is I cap. So you got the expression as here. So the Poynting vector is having a direction I cap. That means the energy is transferred along x direction. That means the wave is propagating along x direction. So S vector S, that is a Poynting vector which vary with the x and t. So here the Poynting vector which is varying with x and t always points in the positive x direction. That is the direction of wave propagation. Now we are going to find out the power, and the average power per unit area will give you intensity. So the power entering, you can consider a receiver in the path of the electromagnetic wave with the receiving area A perpendicular to the z-axis. That means we are placing a receiver in the path of an electromagnetic wave with the receiving area capital A. You can think this to be in a receiver having an receiving area capital A. Now what is the power entering the receiver with the receiving area A? Power is equal to, we had already said that intensity is the average power per unit area. So power is intensity into area. Intensity means a Poynting vector itself. So Poynting vector as into area. We got the expression for Poynting vector multiplied with area. We are taking the modulus value of S, that is E0 B0 by mu 0 sine square omega t minus kx, or sine square kx minus omega t multiplied with area. Now you can replace B0 with E0 by C. So it will be E0 square divided by mu 0 into C. So that is the power. And intensity is equal to average power per unit area. So you can divide it with A and you will get the expression for intensity. That is E0 square sine square kx minus omega t by mu 0 C. That means intensity, that is the average power per unit area, is proportional to, directly proportional to E0 square. which is a general property of waves. We know that the intensity is proportional to the square of the amplitude, isn't it? So E0 is the amplitude of electric field. So intensity is directly proportional to the square of the amplitude of the electric field. That means this represents a wave. And here you can also see that intensity also varies with the time, isn't it? There is a t factor, that is time factor is there. That means intensity varies with the time also. Now you can calculate this intensity by another method, by taking integration, where capital T is the observation time. So P average, you can calculate the average value of power by integrating from 0 to T p dt divided by total time, that is divided by capital T. So again you can take the expression for P from here, you can integrate it and you can substitute the upper limit as T and lower limit as 0 and can divide with the T. So what you will get? You will get E0 square A by 2 mu 0 C. So this is another way to get the average power. Now average power per unit area divided by A means it is equal to E0 square by 2 mu 0 C. That again gives you the intensity. So the intensity of an electromagnetic wave is directly proportional to the square of the amplitude of electric field, or we can say or magnetic field. So proportional to E0 square. Now we will go on to discuss about the important properties of waves. We are discussing about electromagnetic waves, isn't it? We have proved that since the intensity of an electromagnetic radiation is directly proportional to E0 square, we can consider electromagnetic radiation to be a wave. Now these waves are having several properties like interference, diffraction, etc. So now we are going to discuss about that. So first one is principle of superposition. So what happens when two or more waves superimpose each other? When two or more waves pass a particular point in a medium simultaneously, the resulting displacement at that point in the medium is the sum of displacements due to each individual wave. See here you can see the two waves are coming. So the resultant displacement is the sum of these amplitudes of these two waves, and then the waves pass on. That means the waves interfere with each other. So the result of superposition is interference. And this interference of the waves is proved by Thomas Young in his double slit experiment. So what is meant by superposition? The displacement of a medium caused by two or more waves is the algebraic sum of each wave, and interference is the result of the superposition of two or more waves. Superposition of two or more waves results in interference. And you can see that interference are of two types: constructive interference and destructive interference. Constructive interference occurs when a crust meets a crust, or when a trough meets a trough. Now what is destructive interference? And destructive interference occurs when a crust meets with trough, so that there will be maximum amplitude when constructive interference occurs, and there will be minimum amplitude or minimum density for destructive interference. So it was Thomas Young who did the experiment which is known as the Young's double slit experiment, which proved the interference of waves, and he conducted that experiment to prove that light, electromagnetic radiation, has wave-like properties as well as having photon particles. So here you can see that a monochromatic plane wave. A monochromatic wave means it's having only a single wavelength. Such waves are called monochromatic waves. For example, laser. Laser is a monochromatic wave. Such a wave is incident on two narrow slits. Let us see what happens next. The plane and this wave is diffracted by each of the slits, creating wavefronts, cylindrical wavefronts. And you can see here on the screen, on the optical screen, you can see interference patterns, which includes constructive interference as well as destructive interference. That means this slit causes the light from the two slits overlap on the screen, optical screen, producing interference. So whenever two crusts meet each other, we know that it forms the maximum intensity, so that a bright region appears, and this is known as constructive interference. Similarly, there are dark regions also, which are known as dark bands due to destructive interference. So bright bands or bright lines as well as dark lines can be seen on the optical screen due to constructive as well as destructive interference. So this is the experiment again showing the Young's split double slit experiment. So here is we are having a monochromatic light source and it is passed through a small slit and again two slits. So this is the double slits, and from there you can see bright as well as dark lines showing the constructive and destructive interference. The double slit splits the light into two beams identical in frequency and phase. They interfere and form bands on the screen. Now, what is the condition for interference of waves? Constructive interference occurs if the path difference is equal to an integral multiple of lambda. And if the destructive interference occurs if the path difference is an n plus half into lambda. That means odd integral. So here you can see that the path difference delta lambda is equal to path difference delta lambda is delta d, showing the path difference which is equal to n lambda with n is equal to 0, 1, 2, 3, etc. And that is the condition for constructive interference. And for destructive interference, it can be n plus half into lambda or n minus half into lambda. See, from these are the two slits, isn't it? So from here also a light is coming here, and from here also a light is coming here, and there is a small path difference between these two lines, and that path difference, if it is equal to n lambda, then here the intensity of the light will be maximum. That means constructive interference occurs. If that path difference, that is d1 minus d2, isn't it? What is path difference? This path is longer than d2. So path difference means d1 minus d2 is equal to n plus half into lambda. Then that point will be a point of destructive interference. Now we can think of a light, whether it's a particle or wave. If light acts as a particle, if it comes to these two slits, only this can be seen. If light acts as a particle, only two slits will appear on that screen. See, the particle is coming like this and entering the screen. Here also the particle is coming like this and entering the screen. So if we can consider light as a particle, the screen should be like this. But what happens is that the light is diffracting and interfering, making many fringes. So can a wave be particle? In 1887, Heinrich Hertz discovered that the shining light on a metal causes electrons to be ejected, which we had studied as the photoelectric effect. And they noted that The electrons were ejected depended upon frequency and not the amplitude of the light, not the intensity of the light. We already know that energy depends on amplitude. So, in that case, when photoelectric effect was discovered, it is not on intensity that the energy of electrons depend. Energy of electrons depend upon the frequency of the incident light. And years later, Albert Einstein explained Hertz's discovery. That is, electromagnetic waves can behave as a particle called a photon whose energy depends on the frequency of a wave. That means an electromagnetic wave having a particular frequency nu can be considered as a particle called a photon having energy is equal to h nu. So that in photoelectric effect we consider the incident light to be as a photon having an energy is equal to h nu. So it was discovered by Albert Einstein that a wave can also be considered as a particle. So electromagnetic radiation, whether they are waves or particles. Electromagnetic radiation has properties of waves because they undergo diffraction, they undergo interference, isn't it? So they have the properties of waves. But they can also be thought as a stream of particles which are called photons. For example, an example for electromagnetic radiation is light, isn't it? Light can be considered as a wave, and we considered light as a transverse wave which we can filter using polarized lenses. And here light can be also considered as particles called photons because when directed at a substance metal surface, light can knock electrons from that substance, because there in photoelectric effect we consider light as photons, so that on bombarding the photons on the metal surface, the photons are transferring its energy to the electrons. So we are considering light as particles called photons in photoelectric effect. So that's about today's class. We had discussed about electromagnetic waves and its properties like superposition, interference, diffraction, etc. And we also derived the relation for intensity, which is equivalent to the Poynting vector, which is equal to E0 square by 2 mu 0 c. That shows that intensity is proportional to the square of the amplitude. And later on we considered the particle properties of waves also. I think the session is clear to you. Thank you.